Okay, so I'll talk to you about counting short trajectories in ECAs using the transfer matrix method. So I'm a physicist, so I just try to apply some of the stuff I've learned in statistical physics. Okay, so first a very quick recap on cellular automata classifications. Then I will describe a bit more what I mean by counting short trajectories in ECAs. Then I will probably skip a bit more mathematical part of the transfer matrix method, and then see what links I found with Wolfram classification. Okay, so a quick recap. Wolfram in the 80s classified the cellular automata in 4 classes, as you've seen. This is a qualitative classification, so we just looked at them and we say, okay, the cellular automata quickly goes in all zeros or all ones, so it's class 1. There is a periodic structures that appear class 2. It seems random class 3, and you have some kind of long-lived structure. It seems more complex. It's class 4. Okay, but there are still open questions in like how can we classify this cellular automata more formally, even like the simplest ones, the ECAs, and how can we define the complexity of cellular automata. So now Barbara is gone, but there is a work by Barbara and Tomasz Nikolov where she classifies elementary cellular automata depending on the transient length. So the transient length is the time, the number of time steps you take before you enter a loop. And the idea is that simple cellular automata will enter a loop like very fast. Chaotic ones will take a very, very long time before entering one, and complex ones ideally are in between. Okay. And then this was also inspired by another work by Freya, Barbara, and Lemka, where they studied short trajectories in cellular automata on graphs. So why on graphs? Because then you can use a physics method called the cavity method, and from that they compute the number, the entropy of the trajectories that have a given transit length and a cycle of a given length. So yeah, so you just to be sure, so P is the length of the transient, so here it's 1, 2, 3, 4, and then we have a cycle of lengths, so that repeats. Okay, so we will consider like the following probability distribution. So the vector S is one line, the subscript is the time, and then what this probability basically does is, okay, it checks if this state here indeed respects the time evolution. So this is this thing here. And then I also want to know that there is a cycle. So this is this thing here. And then I just add like, I can add Lagrange parameters here if I want to tune. So here I put one on the density of the initial state. Yeah. Okay. And now our goal is to compute the partition function. So if you have no Lagrange parameter mu is 0, then the z will simply count the number of initial conditions that have a transient length p and a cycle of mu c. Okay. A few more usual things of statistical physics. So I define the free entropy phi, from which we do the usual Legendre transform. And we have the density rho, so the density of alive cells in the initial states here. And from which we can get the entropy, and the entropy is related to the exponential leading number term of initial states. Okay, so since we have a 1D chain, we like the first idea is to apply the transfer matrix method, which we usually do as an exercise for 1D spins. So I will briefly describe the case where p is equal to 0 and c is equal to 1. So
can you just remind the p and 0 what they both mean?
P0, it means that the transient length is 0,
okay,
and C 1. So that means stationary states. So if I do this, I just count the number of states that are stationary, that don't change. So in this case, and also in the other case, we can factorize the probability distribution, since the thing depends only on a few things that are before, like this. And then we can apply a transfer matrix, which is basically we rewrite this thing here as a function of this matrix here. I won't enter into too much detail, but then we can just find that the partition function Z it can be written as a trace of a matrix to the power n. We take the thermodynamical limit, so n goes to infinity. So this will be dominated by the largest eigenvalue. Okay.
N is the number of cells, right?
Of cells, exactly. So from now, the number of cells goes to infinity. Yeah, technically, when I do this, I have periodic boundary conditions, but since it goes to infinity, it doesn't really matter. And the procedure can be expanded. So now, instead of having only, so in this matrix here, the index is basically like are given by these pairs of numbers. So if you have 0, 0 here and 0, 1 here, you will have 0, 0, 1 because the two middle ones must match. And then, as you see, most of the matrix will be sparse, but it will still be a very big matrix relatively short. But maybe we can still get interesting things from that. Okay. So okay, now to the results. So class 1, the idea is that it quickly goes to a homogeneous configuration. So we take C equal to 1, which will give a configuration that does not change. And I will increase the transient size P and look at what entropy I get. And what is expected and what we get is that relatively fast for all the rules will reach the maximum possible entropy. So log 2, because it's normalized by n.
So here the entropy is a proxy of the number of initial states that
Exactly.
give you this transfer.
Exactly. So yes, so for most rules we get really fast to the maximum entropy. And what we can see is so for instance for rule 168, it gets less fast, which means that there are like more like initial states that will give like structure that are long-lived. But we expect that if I increase this, it will take into account more and more of this structure and go to the full.
So when you have the maximal entropy, this means that any initial state give you.
Yes.
So this is number of transients of P smaller or equal than. Sorry. So I don't understand. So if you have maximum entropy,
yes.
It means that any initial state satisfies.
Yes, exactly.
But the P being fixed, it means that the transient should be at most 2? Or?
So you can have a loop into the transient. So if you loop...
okay,
I see. So I mean...
I see. So if you have a transient of 1, it also counts for the transient of 2.
Exactly.
Okay,
so yeah. So if you look at the probability distribution, I just check like once if there is a loop. Okay. But there can be many other
That's why
loops.
It's strictly increasing. Yes.
Exactly. Yes. But yeah, otherwise you would have to check other things. And
okay.
Okay. Then another thing. So in the other case, if I then mention it, it's just mu is equal to 0. But I can also change mu, and so I will obtain different densities and the entropy of like an initial state of this given density. So for instance, I mean this can like give a few indication of, for instance, in this case, if you have like a very sparse initialization around here, we see that it's very fast, it's a full entropy, so you will have almost no pattern. But if you increase it here, you see that you will have like this long pattern because like the entropy is low here. Or I mean here it's just jumps from here to here because you would have to find like really to fine tune the mu, and you only have like the convex envelope when you do the Lagrange transform and all that. Yes. Okay, now for class 2, there is a small additional difficulty, is that you can have patterns that are shifted like this, but that are still like periodic and visually easy. So for that, instead of looking at like a thing like this, I can just shift the considered neighborhood when I do when I build the transfer matrix.
Mm-hmm.
And I do the same for like the other thing, and you can also do by block, like one block, like one down, one right, and things like this. If you for the structures that can appear, so that I can because otherwise it will give like a very small entropy, whereas it's still easy. Okay, so for class 2, I found a bit more variety in what happens. So there is like an easy case like this where the entropy goes very fast to the maximum entropy. And then we have some rules like these two where we see kind of structure appear. So the entropy still seems to increase, but more slowly. So yeah, that kind of indicates when there will be like more like long-term patterns. And I mean, we could also discuss. I mean, if this is like really rule 2, I mean, there seems to be like strange thing happening. For me, it's not trivial to see that this is in rule 2. Okay. And then for class 3, what I found is that most of class 3 go to a minus infinity entropy, so no solution for the given PNC, 0, so sub-exponentially many, or a low entropy, so the maximum was around 0.4. Maybe interesting thing I noticed is that if you have like the neighborhood with no translation, so translation left or translation right, you go to the same entropy, which intuitively could indicate that, I mean, it's chaotic, so it doesn't change if you look left or right or stay the same. And additionally, maybe an interesting thing to notice is that all the rules in class 3 that have positive entropy were classified as class 2/3 in Barbara's paper. So there is also maybe a link there. Okay, and for class 4, sadly, I don't really have a way to differentiate them from class 3. For one of them, at least, we didn't have this property that the entropy is the same in each direction. So maybe that could be investigated. But yeah, I wanted here to put a figure with all the rules, but the simulation is still running. So we just have a subsample of rules. But yeah, from what I've seen, like class 1 and 2 will all be here.
Yeah.
Class 3, most of them will be here, a few of them here, and class 4 change. Yes. And that's it. I'm not sure.
You still have some time if you want to wrap up, but
yeah. So basically, what I did is extend the transfer matrix method to compute the entropy of short trajectories. What I saw is that class 1 quickly reaches the maximum entropy as expected. If we include translations, most of class 2 quickly reaches this maximum entropy. Some exceptions, but we still have this general trend that the entropy increases as P increases. For class 3, this doesn't seem to be the case, so it seems to plateau or be 0 or minus infinity. And for class 4, we also have this finite entropy that plateaus. But I should go to be a bit larger time steps. But yeah, you have very large matrices. My code is not fully optimized, so we can go a bit further, but it's still exponential. So we cannot go much further than that. And then some interesting things to do. You could change the Lagrange parameters. So you could vary if you want check a certain activity. So if there is like a lot of changes in between the steps, or if it's relatively the same, maybe that could give an indication of the complexity of the okay, that's it.
questions? I have quite a bit of questions actually. So the first one is so this parameter mu. I'm not too sure I understood what is its job in the distribution.
Yes. So if you only have 1 here, you uniformly sample from the things that respect this.
Yes.
if you put mu big, you will sample more the
one which
states.
have live ones.
Exactly.
Which are more alive.
Exactly. So it's exactly a chemical potential.
Okay.
If you want to, or you can also, I mean, it's also a temperature depending on how you see these things.
I see.
But yeah, you can also imagine this as a magnetization if you want. I mean, if it's spin, you will have some magnetization here.
Okay.
Yes.
Because, for example, just with this mu, so if I take the rule and then the rule where you flip the black and whites,
yes.
So they would have a very different distribution of sampling, right?
Yeah, if mu is not 0, yes.
Okay. So in your experiment, what mu did you take?
So mu was 0,
okay,
except for the one case here, because I wanted to see what happens if for typical configurations, which are the initial configuration, which have 0 and 1s.
Okay.
But yeah, one of the things I hoped for was like some kind of phase transition where I see that at a specific density you see thing appear, but I didn't find anything like that.
Okay. Right. So the other question is, so in your graph where you show P, I mean the entropy versus P. Yeah, any of these ones, yes. So in that case, you are integrated. So this is for C equal 1 for everything.
And for the other ones, what I did, so typically, if I take the last one here, I tried different C's, different P's, and I took the maximum that I got. From that.
Because you could also think to average over C's, for example. Would this make sense or not? Because in a sense that, I mean, connecting to Barbara's paper, I'm not too sure, but for it was just the transient, and the cycle length didn't matter.
Yes, exactly.
So this would be equivalent to, to take the maximum, that's what you're saying.
I mean, the thing is, it's the entropy, so you have to take the maximum, because everything that else will be exponential. So I mean,
another question I had is, so how do you diagonalize these matrices? Numerically or?
Yes, so basically I compute all the, so it will be this really big matrix here, all the thing, and then I like
multiply
in a sparse thing, most of them will be 0, and then I use a sci-fi method of computation. I only need the largest size with sparse matrices, so it's relatively optimized.
So if you compare kind of the complexity of this algorithm, diagonalizing or finding the biggest eigenvalue, versus doing what Barbara did, which is actually simulating the thing, it's faster, right? Or
I mean, the thing is, technically here, it's like infinite size cellular automata since n goes to infinity.
Right. Okay.
So
I see. Yeah.
So it's we can do for finite n.
Yeah.
I'm not sure how it compares, but I mean, what is like good here is that there is no stochasticity in the initial condition. So yeah, that's what I wanted to do, is like to have something like more concrete, even if like that's powerful.
Okay. And the last thing was with this translation, you say that you look at the translated part. So in this case, you didn't detect some sort of translation happening. You just try with the two possible translations, and then you look at the entropy, and then you use that. Okay. Okay, I had one last question, which is about the cavity method, but I don't know how much it is related to that. So the question is, what is just a high level? What is the cavity method?
So on graphs specifically, maybe. So the idea. So the idea is typically if you have a system like this where like this thing must respect, has some interaction with his neighbor. What you can do, it's kind of a mean field thing. So it's saying if I want to compute like this thing here, I will like cut all this part of the graph here, compute it like knowing these two and trying every possible thing here, and then you can like build from.
Replace it by the average of the.
Yes, exactly. So it's kind of yeah.
I see.
But
Okay.
I mean, I can go into more details.
No, no, it's fine. It's fine. I was just wondering, is it? It's not at all related to these transfer matrix methods.
So
or is it?
yes, in 1D the methods are equivalent.
Okay, I see.
Yes.
Okay.
But because the thing is, in 1D, for this to work, you don't want loops.
Okay.
Because otherwise you have the correlation.
Okay.
And since it's 1D, you only have a chain
I
of
see.
spins, so we don't have that.
I see. Okay. Thank you. Any other questions? Okay. Thank you, everybody.